One, two, three. So welcome to all. Myself, Dr. Santhosh Singh, working as an associate professor in Department of Physics, Institute of Aeronautical Engineering. So my today topic is density of state in quantum well structure. Okay. So we already discussed about density of state in bulk semiconductor. So first we will see what is the quantum well structure. So okay. So quantum well, this is your quantum well structure. This is your bulk structure. So what is the difference in quantum well and bulk structure? See here, your bulk structure is defined or expanded in all the possible three directions. But what happens in the case of quantum well structure? You restrict the growth of this structure in one particular direction. Means, suppose if this is your positive x direction, this is your positive y direction, and let's suppose this is your positive z direction. So what you are doing here for getting the quantum well structure, you restrict this growth. You are restricted the growth of this crystal structure along the x direction. You confine this crystal structure in x direction. Means whatever the particle, means electron, free electron available inside this crystal structure, if you restrict the growth of this crystal structure in x direction, what happens? That particle cannot move in this x direction. The direction of free particle is now restricted and it can only move in along the y direction and along the z direction. Okay, but it cannot travel in this x direction. So what you are doing, you are restricted the motion of free particle or electron. So such type of geometry is considered as nanostructure. And if you are confining one particular direction, means if you are getting the 2D structure, what is the best example of 2D? A kind of seed like that. So such type of geometry is considered as a quantum well structure. So what will be the density of state in quantum well type of structure? We already discussed the density of state in bulk case. Means where all the possible direction, the crystal can expand, growth can be happen, and whatever the available free electron inside the material can travel in all the possible directions. Such type of study is considered under bulk case study. But if you restricted any one dimension of that crystal structure and other two dimensions are as free as bulk, so such type of structure or such type of case is known as quantum well structure. So in the case of quantum well type of structure, what will be the density of state? Okay, so we already discussed the density of state for bulk material, where the degree of freedom is 3. One other thing I missed. Here in quantum well structure, the degree of freedom is 2. Here see in the bulk structure, the degree of freedom is 3. Means in all the possible 3 directions, the electron can move. But in the quantum well structure, the electron can move only either in this case, either in z direction or in y direction. Because you restricted the motion of electron in x direction. Because your crystal is not grow in such particular direction. So how the electron can move beyond the crystal structure? Okay, so means the degree of freedom is 2. Means you confine the one direction. Okay, so just I said, we already discussed the density of a state in the bulk semiconductor or crystal structure, and what we get the rho E, rho ED This is the normal expression of density of state or rho k dk in term of wave vector k. So rho e d for conduction band. Why? Because particularly your band structure is divided in two category. One part is known as conduction band. The other part is known as valence band. So for balance in conduction band, what will be the density of state? Density of state means number of available state in energy range E to dE per unit available volume or per unit volume of given semiconductor crystal. So for conduction band, this is your conduction band. So what will be the available energy state in E to E plus dE energy range per unit volume? So we already derived this expression, and what it is 1 upon 2 pi square multiplied by 2 mc, where mc mass of effective mass of electron in conduction band, where conduction band. So 1 upon 2 pi square multiplied by 2 mc upon h cross square whole to the power 3 by 2 E minus EC. E minus EC. What is EC? EC is nothing but band age energy. Band age energy means the lowest energy in conduction band region. Lowest available energy in conduction band region. Okay. Whole to the power half means what you are getting here, this density of state is varying according to E, because EC is constant. This for any particular crystal structure, this band age energy either in conduction band or valence band is constant. So what is the variable term? See here, all this 2 pi mc conduction effective mass of electron in conduction band h cross square, all are constant. So what is the variable? E, and your density of state rho E is now varying according to what? Rho E, you can say, is proportional to e to the power half, right? So if you plot this variation, you will get a curve like that. Okay. So if you take the energy axis here and density of the state rho e d on this axis, so it looks like that. Okay. If you take the density of a state on this axis and energy on this y axis, it will looks like that. So nothing to be here for confusion. Okay. So this is the density of a state expression for conduction band region. Okay, for any given bulk semiconductor or any kind of material. Now see, in valence band region, this V represent the valence band. So rho E is equal to nothing but 1 upon 2 pi square 2 mb upon h cross square whole to the power 3 by 2 EV minus E whole to the power half. Again, you can say that in the valence band region, our density of state also vary according to rho VE, also vary according to e to the power half. Okay. So in both case, for bulk semiconductor means in the conduction band region and in valence band region, your density of state vary according to e to the power half. So this is the expression in term of energy, and but actual our derivation came in term of wave vector k, and that is rho k dk is equal to what? K square upon pi square dk. And from this expression only you can derive these two expressions. We already discussed how you derive. Actually, E is equal to what? EC plus HC square upon 2m, P square by 2m, P square by 2m. P is nothing but H cross K. So H cross square k square upon 2mc. So using this expression from here, you can use this expression here. You can get this thing. Okay. This is for conduction band. For balance band, E is equal to EV minus H cross square K square upon 2M H star. This MC star is what? Effective mass of electron in conduction band. This MH star is effective mass of holes in valence band. So using these two equations along with this equation, you will get this equation. So what is this? This is also a density of a state in term of wave vector k. What is this? This is also a density of a state in the term of energy. So first we derive this expression, and with the help of this expression we can deduce this density of state in term of energy while using these two additional equations. Okay, and here what we got? We get the density of state vary according to e to the power half, means under root e in the case of bulk semiconductor. Now, but what is my aim? My aim is to derive the density of state in quantum well structure. So we already discussed what is the quantum well structure. So let's move ahead. So already it is written what is quantum well structure, and I already discussed. I reduce the dimension of the semiconductor in one direction. In one direction. What he is telling? He reduced the direction of semiconductor. Let's suppose this is your semiconductor crystal, and inventor or whatever the. So if you reduce the dimension of this considered semiconductor in one direction, what you will get? You get a kind of thin sheet structure that is also known as 2D structure, and that structure is considered your quantum well structure. And that the same thing is written here. If I reduce the dimension of the semiconductor in one direction, say let's suppose Z direction, and make it a thin sheet, then the correspondingly the density of a state change. In Z direction, the density of a state will be changed. But Kx and Ky still have a very large number of value, but the allowed values for Kz become highly discretized. Means what he want to say? We already did, when we are computing the density of a state in bulk semiconductor, just give me 1 minute. So let's suppose this is your bulk semiconductor and having the dimension in X, in Y, and in Z. What? In this considered semiconducting crystal structure having the dimension Lx in X direction, Ly in Y direction, Lz in Z direction. And once we solve the available allowed energy states, available solution for electron wave function in term of k, what we got? We got the k value are what we found? We found that the k values are discrete in nature. So what is k? K is a wave vector. Vector means this k have a 3 component: kx, I, ky, j, kz, k, ij, k cap. So this kx, ky, kz is the component of this wave vector k, and we found that this k have a discrete in nature, means these kx, ky also will show the discreteness or discrete values in x, y, and z direction. So this is the case of bulk. And what are the possible value of kx, ky, kz? The possible value of kx is what? Pi upon lx multiplied by m, where m is integer, The possible value of ky was pi upon ly multiplied by p, where p is also integer, and possible value of kz was, I am discussing the case of solution of electrons wave, finding the solution of electron wave function, or getting the electron wave function in term of k, and that time we got this wave vector k values. Wave vector k have the value which are in discrete in nature, and if k are discrete in nature, their corresponding kx, ky, kz component will be also discrete in nature. And what are these values? It will be, kx will be pi upon lx multiplied by m, pi upon ly multiplied by p, pi upon lz multiplied by q, where m, p, q all are integer. So let's say if m is equal to 1, so the least possible value in x direction, least possible value of kx in x direction will be what? Pi upon lx. Then next value will be 2 pi upon lx. Like that. So means these are discrete values. Okay. So if all are discrete in nature, means k will be also discrete in nature. But in particular case, means in the case of quantum well condition, what you are doing? You are restricted the motion of electron in z direction. Means even you are restricted the growth of the crystal in z direction. This z direction crystal you are not able to see. It looks like a sheet or plate, thin plate, where this is x, this is y. This entire z direction growth will be gone. Okay. Now your electron can move in this xy plane only. Okay. It cannot move in the other available third direction, that is z direction. Okay. So what happened? These kx, ky will have a same value, like pi upon lx, pi upon ly. But in the z direction, you can't say z is 0. It will be infinitesimal small. So if it is infinitesimal small, Lx is what? Length of the crystal structure in x direction. Ly is what? Length of the crystal structure in y direction. Lz. And if you are if you are considering the case of quantum well structure, this Lz will be infinitesimal small. Then pi upon Lz. Lz is not 0. It will be very, very small. So Lz will be small, then the value pi upon Lz will be very, very large. So if the first value, suppose this is x, this is y, this is z. So first value pi upon Lx, as it is like bulb, 2 pi upon Lx, as it is like bulb. In y direction also same, pi upon Ly, pi upon Lz. But now in the case of quantum well structure, and you confine the structure in z direction, then what will be the pi upon Lz? Pi upon Lz is like that. Means it will take a very large value, and if the available range is from this much to this much, you will get only 2 or 3 possible set of value, like pi upon Lz, 2 pi upon Lz. But pi upon Lz will be lie here. The next 2 pi upon Lz will maybe at the end of the available range. But in the case on the x-axis, you can get too many number of available state, like a bulk case. So what I mean to say, these value will be now highly discretized, discrete in nature. You can say exact number 1 or 2 or 3, very, very few. states will be available in the z direction range. Okay, means it will be highly discretized in the nature comparison to x and y z comparison to x and y direction. So what will happen? So if such case will occur, so how you will compute the density of state? So for the bulk case, your wave vector is like that, where k is, this is your wave vector for bulk case, where the projection of this k vector will give the kx, ky, kz component. Kx, if this is x, ky and kz. So this k have now increment in like this direction. Means suppose this is the angle theta. So this can increase in this direction. Means all the value of ky, kx, kz are possible in bulk case. So it will create a kind of possible set of values, and these possible set of value will create a kind of sphere in the bulk case. But in the quantum well case, what will happen? Only 2 or 3 sets are available in z direction, z value, kz value. Like this is, let's suppose, pi upon Lz. This is 2 pi upon Lz. So let's suppose this is the first value we are taking. So your k vector will be always lie on this plane, and this plane is cutting this z axis at what? At point pi upon Lz. Means this plane is perpendicular to z axis and passing from z axis upon pi upon Lz. And this k vector will be, this k vector tip will be always lie on this plane. Okay, because it cannot take too much value for z. Okay, either it will take this pi upon Lz, and in next case maybe pi upon 2Lz. But the no next value are possible for quantum well case. Okay, so you have to be restricted with your wave vector such that this tip of this wave vector k will be always lie on this plane. But correspondingly, they don't have any effect on the value of kx, and ky. Okay, so now in this case, your considered region is what? This plane. Okay, now you have to focus on this plane, which are cutting the z axis at pi upon Lz. Means it is perpendicular to xy, it is parallel to xy plane, and perpendicular, and it will cut the z axis perpendicularly at pi upon Lz, at the point pi upon Lz. Like in the bulk case, what will be the your area of concern? Your area of concern will be a whole sphere. But here, your area of concern will be a kind of plane which is passing from z axis, okay, and parallel to the xy plane. and it will actually bisect the z axis at pi upon Lz perpendicularly. Okay. So now in this case, your area of concern is this plane where the k vector tip will be always lie. Okay. Now the wave vector k, like a bulk case, you can write the wave vector k like I k x plus j k y plus k k z. So mod of k square will be what? Kx square plus ky square plus kz square. But see here, this kx and ky will not change. It can actually it will be these kx and ky component will take the random value, but this kz will be always fixed. That's then only you can govern a kind of plane. Okay, means suppose this wave vector have a fixed z value, but it can take any value of x, y, and z. Like if this is the case, and let's suppose this is the first case, then your x and y is this. This is the second case, then your x value is this, y value is this. If this is the case, you have to draw the perpendicular in this negative quadrant region. So you will get the corresponding x and y value. So what I am trying to say, x and y will be changed actually, but z will be not changed. Okay. So this x and y will be actually the, let's suppose this is your plane. So this x and y for this plane is what? Transverse component. Okay. Kx and ky. So you can write this kx and ky because due to variation of x and y only, you will get the variation of density of a state. Why? Because this z values will be fixed. So you can write this expression, mod of k square expression, as a kt square, means transverse component of that particular plane plus kz square. Okay. So this is your first equation. Now, what will be the energy expression? Energy expression is, I already wrote, E, normal energy expression for conduction band and valence band is E is equal to EC plus H cross square K square upon 2 MC. For conduction band, E is equal to EV minus H cross square K square upon 2 MH star. MC star. This MC is nothing but effective mass of electron in conduction band. MH star is effective mass of hole in valence band. Now see here, in this energy expression, the K square term is used. Now this K square, this energy expression, you can write this energy expression in term of their component. Component of K means what I am trying to say. You can write this E in conduction band region like E is equal to EC plus H square Kx square plus 2 MC H square K Y square plus 2 MC plus H cross square Kz square upon 2 MC. This is for conduction band region. For valence band region, E is equal to EV minus H cross square Kx square upon 2 MV. Similarly, actually take a bracket here, plus H cross square Ky square 2 MV plus H cross square Kz square 2 MV. Now, this Kx and Ky is what? Kt square. So, you can write these two terms separately. E is equal to EC plus H cross square KT square 2MC plus H cross square kz square upon 2MC for conduction band region. Similarly, for balance band region, you can write. Okay, means what is KT? KT is nothing but a transverse component for that particular plane where your K vector will be moved, where your K vector tip will be always lie, because the Z value will be always constant, and what will be the change only? Only the X and Y value will be changed. Okay. See here. So this is your considered plane, and this is your X direction, this is particular Y direction. So these X and Y is what? Transverse direction for this particular plane. Now this KZ is what? Just coming out perpendicularly from this plane. Okay. So this considered plane, this circular plane actually, or any kind of plane, is what? It will, this X and Y direction, Kx and Ky direction is lie in this plane, but this Kz direction is coming out perpendicularly from this plane, and this plane will cut the Kz axis at what? Let's suppose pi upon Lz. Okay. Now, this is your area of concern region. Okay. Like in bulk case, what will be the your area of concern? Your area of concern was a kind of sphere, and you considered only positive octant of that sphere. So you can see my previous video. So here your area of concern of this plane, and and your aim is to find out the density of state for particular quantum well structure. So for you know the definition of density of state. So density of state is nothing but available number of state in the region E to E plus D, in the energy range E to E plus D per unit available volume. This is the definition of density of state in term of energy. In term of wave vector K, available number of state in K to K plus dk region per unit available volume. Okay, so this is your K space region. Okay, so now suppose this region in this plane, this first circle is representing the K region. Now this second circle is representing the KT plus DKT. Why? Actually, this is your plane where all the thing is happening. So actually this is the plane. But the same thing, here only X and Y will be changed. Means if X and Y only will be changed, then what happened? You can say that X and Y like KT and DKT. Means even you are moving on this plane, you can consider the value of X and Y from here. Okay, the same value you are getting for X and Y in this plane also, whatever the value you are getting here. So that's why I am taking this KT and KT plus DKT, means this T represent only, there are only variation in X and Y component, transverse component of this plane. So suppose this is the region of defined by KT radius, wave vector KT. Now this whole region is defined by KT plus DKT wave vector. So in between this region, KT to KT plus DKT is what? This region, this shaded region is governed by K to K plus DK region, or KT to KT plus DKT region is what? This region. this region. So now what will be the area of this region? So area of this region will be 2 pi kt dkt. How? Now cut this strip. It looks like a strip. Now cut this strip and straight it. Okay. So what will be the length? The length of this strip will be the circumference of this circular kind of thing. So what will be the circumference? 2 pi kt. So this length will be 2 pi kt. Now what is the width? What is the width? dkt. So it is a kind of rectangle. So 2 pi kt is acting like a length and dkt acting like a breadth. So 2 pi kt multiplied by dkt will be the available area for computing the density of a state. Okay. So this much is the area available in the state, in between the state k to k plus dkt. Okay. Now, so in term of t, transverse vector, rho k dk is what? Density of a state. So because only x and y component are varying there, that's why we can write this rho k dk as rho kt dkt. This t will be in the suffix. Now this is your available area. If but like bulk case, what we consider? We consider the only positive octant of considered region. So here, this is the case of disk. So we will consider the positive quadrant of that disk. Why? Because this is a 2D geometry. In the bulk case, that sphere is 3D geometry. So if you want to choose the only positive area of that sphere, you have to choose the positive octant of that sphere. But in 2D geometry, if you want to choose the positive region of that 2D geometry, you have to choose the positive quadrant, not octant, because this is the 2D geometry. So positive quadrant is what? Suppose this is x, this is y. So this is negative y, this is 0, 0 origin. This is positive x, positive y. This is negative x, negative y. So what will be the only positive value? This is. So this one is what? Positive quadrant. In other, some value, sometime the x value will be negative, sometime y value will be negative, sometime both x and y will be negative. This is the only region where the both x and y will be the positive. So that's why this is the positive quadrant, 1/4 of this whole region. So we have for computing the density of state, we always take into the consideration of positive values of k. So for getting the positive value of the k, you have to divide 1/4 of whatever the available area, and that available area is what? 2 pi kt dkt. So 1/4 is representing the, means we are choosing only the positive quadrant, multiplied by 2. Multiplied by 2 is representing the, we are taking into account of also the electron spin, because electron have two type of spin, up spin and down spin. So that's why we multiplied by 2. There are if for particular single electron, there are two possible states, one for up spin and one for down spin. Okay. So this is the case. Now your available area is now this much, 1/4 multiplied by 2 pi kt dkt multiplied by 2. This is your available area. Now if we know the area of single state, this is the total available area which is 1 by 4 multiplied by 2 pi kt dkt, and again multiplied by 2. Why 2? Because we are taking into account of electron spin. So suppose this is the available area. Now how many states can be available in this available area? So suppose any single state have this much area, then what will be this much area? You have to tell in the number or in some expression. So in x direction, the lowest possible value of k is what? Pi upon Lx. In the y direction, the lowest possible value of ky is what? Pi upon Ly. So this is a kind of, this will construct a kind of rectangular, and this rectangle area will give the value of area of our single state. Why? Because only variation of Lx and Ly will give the variation of k. So what will be the possible least possible value of kx? It is pi upon Lx. What will be the least possible value of ky? It is pi upon Ly. Then what will be the least possible value for single state which is governed by these wave vector kx and ky? So the area of least possible state is what? Suppose this is pi upon Lx, means A is equal to pi upon Lx, B is equal to pi upon Ly. So area of rectangle is A multiplied by B, means pi upon Lx multiplied by pi upon Ly. Okay. So the area of single state is what? Pi upon Lx multiplied by pi upon Ly. So suppose I know the total available state. Okay. Now I also know the area of one single state. So if we divide the area of total available state by area of one state, pi upon Lx multiplied by pi upon Ly, what it will give? It will give the total number of states available in this considered region. Okay. Now if we again divide this whole number by per unit volume, means Lx, Ly, Lz. Okay. This is our bulk. This is our quantum well geometry, where in x direction your sample size is Lx. In y direction, your sample size is Ly. In z direction, your sample cannot be grow, but you can't say it is 0. So definitely it is some z direction, some z dimension also, z direction dimension also. So Lx multiplied by Ly multiplied by Lz, and if we divide this whole number by this volume, so this thing will give the density of state for quantum well. Why? Because what is this? This is the available number of state in the region k to k plus dk. So density of state definition is what? Available number of state in between k to k plus dk per unit volume. So this upper term will give the available number of state in the k to k plus dk region divided by per unit volume, means whole volume Lx, Ly, Lz will give the density of state for quantum well structure. So after cancelling all this term, what you will get? You will get rho k is equal to rho k dk, or in term of transverse vector, rho kt dkt is equal to kt dkt upon pi upon Lz. So see, density of variation, density of state for quantum well structure will be depend on Lz, dimension of the specimen or crystal structure in z direction, where you confine that crystal structure. Okay. So that's all. Thank you. So that's all for today video lecture. We will deduce some more expression based on this formula in next video lecture. Thank you. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.